Voyager 2 is 12 billion miles away, running on less power than your kitchen nightlight, and it just broke science. Not advanced science, foundational science. The kind of science that took decades to build and was considered settled. What this 47-year-old spacecraft found beyond the edge of our solar system forced physicists to reopen closed questions, discard published models, and admit something deeply unsettling. The space between the stars is not what anyone thought, and we are only beginning to understand what that means for us. There is a moment in every great scientific story where the evidence stops confirming what we believed and starts demanding that we believe something else entirely. That moment has arrived for our understanding of the solar system. It did not arrive with a press conference or a dramatic announcement. It arrived quietly in streams of data transmitted at 160 bits per second across 12 billion miles of cold vacuum from a machine that should have stopped working decades ago. And most people completely missed it. Voyager 2 was launched on August 20th, 1977. The mission was never supposed to be historic in the way it became. The original plan was straightforward by the standards of space exploration. Fly past Jupiter, collect data. Fly past Saturn, collect more data. If the spacecraft survived, attempt flybys of Uranus and Neptune. Total mission duration, 5 years, maybe 10 at the absolute outside. The engineers who built it were not designing for eternity. They were designing for a planetary survey mission with a clearly defined endpoint. Nobody in that control room believed they were building something that would one day cross into interstellar space and deliver the most disorienting scientific data in the history of planetary science. But that is precisely what happened. And the reason it happened is because the people who built Voyager 2 built it with a level of precision and care that outlasted every expectation placed on it. Voyager 2 did not fly alone either. Its twin, Voyager 1, had launched 16 days earlier in September 1977. The two spacecraft were designed to ride a rare planetary alignment, a window that only lines up once every 176 years. The lineup lets one robot swing from one giant planet to the next, stealing a little momentum from each one with a slingshot gravity assist, instead of carrying enough propellant to fly direct. No mission of this scale will be possible again until around the year 2153. The window is the reason the Voyager program exists, and the backup of having a second probe cross the same boundaries years later is the reason the magnetic field puzzle carries the weight it does. By the time you finish reading about what the spacecraft discovered, the picture of our solar system you carry in your head will be permanently altered. Not updated, not refined. Altered. Because what Voyager 2 found is not a minor correction to existing models. It is evidence that the fundamental architecture of our cosmic neighborhood is more complex, more dynamic, and more mysterious than any of the frameworks we built to describe it. We will walk through 3 layers. First, the heliopause crossing of November 2018. Second, the Uranus reanalysis of November 2024. Third, the shape of the heliosphere and what still lies ahead beyond it. Taken together, those 3 layers are rewriting what school textbooks will need to print in the next decade. Let us start with the boundary itself, because that is where the story begins and where the first shock arrives. For most of the 20th century, scientists operated with a reasonably confident model of where our solar system ends. The boundary was defined by something called the heliopause, the point where the solar wind, that constant invisible stream of charged particles exhaled by the sun in every direction, finally loses enough energy to give way to the interstellar medium, the thin sea of gas, dust, and magnetic fields that fills the space between stars. The sun, in this model, was essentially a vast pressure system, constantly blowing an outward wind that formed a protective bubble around every planet, every moon, every asteroid, every comet in our solar system. That bubble is called the heliosphere, and the heliopause is its outer wall. The idea sounded clean. It felt intuitive. It gave school textbooks a tidy chart with arrows pointing outward into an otherwise quiet cosmic ocean. For 2 generations of researchers, that chart was the truth. And then the probes crossed the wall, and the chart broke. On November 5th, 2018, Voyager 2 crossed through the heliopause and entered interstellar space. It became only the second human-made object in all of history to achieve this, following Voyager 1, which had made the same crossing 6 years earlier in 2012. The confirmation was not ambiguous. 4 separate instruments aboard the spacecraft registered simultaneous and dramatic shifts in their readings at the same moment. The cosmic ray detector recorded a sharp and sudden drop in high-energy particles streaming outward from the sun. The plasma science instrument, a working detector that Voyager 1 no longer possessed, registered a complete cessation of the solar wind. The magnetic field sensor registered a shift. The low-energy charged particle instrument registered its own shift at the same moment. The spacecraft had crossed the line. Scientists expected interstellar space to be quiet. That was the word that appeared repeatedly in the theoretical frameworks built over decades of research. Quiet, sparse, cold, a passive backdrop through which the Voyager probes would drift without incident, their instruments registering the thin, uniform, undisturbed medium between the stars. The expectation was not unreasonable. The space between stars really is thin. The particle densities really are tiny compared to what we have inside our solar system. The textbook picture of a gentle cosmic sea was not crazy. It was simply incomplete in ways that nobody had anticipated. The reality was something categorically different. And the first indication of just how different came from a temperature reading that genuinely shocked the research teams analyzing the data. As Voyager 2 crossed the heliopause, its plasma science instrument recorded a temperature reading from the plasma just outside the boundary. The number that came back was 54,000 degrees Fahrenheit. 54,000. In the thin, sparse, supposedly cold region of interstellar space immediately beyond the edge of our solar system. That number was not a malfunction. It was not a calibration error. It was confirmed and reconfirmed by the research teams at the Jet Propulsion Laboratory in Pasadena and by independent scientists reviewing the transmitted data. And it was significantly, substantially hotter than the theoretical models had projected. Now, the plasma out there is extremely diluted. It is so thin that the heat does not transfer the way it would in a denser environment, which is why the spacecraft itself faces no danger from it. The probe is not being cooked. The number reflects the temperature of the charged particles, not the kind of heat that would melt metal. But the temperature reading alone forced a significant and immediate revision of how astrophysicists model the boundary region between our heliosphere and the broader galaxy. The interstellar medium just beyond our solar system is not the cold, passive environment the textbooks described. It is something hotter, more energetic, and more active than any of the dominant models had predicted. But the temperature was only the beginning, because waiting just beneath that first layer of data was something even more difficult to explain, something that went directly to the heart of how our solar system formed and how it exists within the broader galactic environment. That something was the magnetic field. And what Voyager 2 found about it, in combination with what Voyager 1 had found years earlier, created a puzzle that researchers are still working to solve today. The pre-Voyager models of the heliopause predicted a clear and logical magnetic geometry. Inside the heliosphere, the magnetic field is shaped and dominated by the sun. Outside the heliosphere and the interstellar medium, the magnetic field belongs to the galaxy, shaped by entirely different forces over incomprehensibly long timescales. These two fields, the solar and the galactic, should have been oriented in meaningfully different directions. They should have met at the heliopause like two separate systems encountering each other at a border, misaligned and distinct. That was what the model said. That was what decades of theoretical work had predicted. What both Voyager 1 and Voyager 2 actually found when they crossed the heliopause was alignment. The magnetic field lines inside the heliosphere and the magnetic field lines just outside it were pointed in essentially the same direction. Both probes, crossing at different times and at completely different locations along the heliosphere's perimeter, confirmed this alignment independently of each other, and scientists do not fully understand why. This was not a prediction that appeared in any of the major models. It was not an anticipated result that researchers were watching for. It emerged from the data without warning, and its implications for how the sun's magnetic influence interacts with the broader galactic field, and for how our solar system fits within its galactic environment, are still being actively worked through by the research community. Think about what that means for a moment. Two spacecraft sent out decades apart, crossing the boundary of our solar system at different points separated by enormous distances, and both of them finding the same unexpected magnetic alignment that nobody predicted. That is not a coincidence that can be explained away. That is the universe telling us that our models are missing something fundamental, something that sits at the intersection of solar physics and galactic structure, and that we do not yet have the framework to fully describe. The assumption embedded in most pre-Voyager models was that the boundary between our heliosphere and interstellar space would be sharp and well-defined. A clear transition point, like a surface, like the edge of a body of water, where the environment on one side is categorically distinct from the environment on the other. What the Voyager data revealed instead was something far more complex and far more difficult to model. The heliopause is not a wall, it is a membrane, a permeable, dynamic, constantly shifting interface where two massive cosmic pressure systems meet and interpenetrate each other. Particles from inside the heliosphere are escaping outward beyond the heliopause. Particles from interstellar space are penetrating inward. The boundary leaks in both directions simultaneously. And Voyager 2, with its functioning plasma science instrument, was the first spacecraft in history capable of measuring this phenomenon as it actually occurred in real time. The data it returned forced researchers to substantially revise their understanding of how our solar system's primary protective shield actually operates at its outer edge. This is not a detail. This is not a minor technical footnote in a scientific paper. The heliosphere is the structure that has shielded life on Earth from the galaxy's most lethal radiation for billions of years. The high-energy cosmic rays that stream in from distant supernova explosions, from neutron stars, from some of the most violent events in the known universe, these are held at bay by the heliosphere. The strength of that shield, the integrity of the heliopause, the rate at which cosmic rays penetrate it, these questions are directly connected to understanding what kind of radiation environment Earth has inhabited over its 4.5 billion year history. They are connected to understanding what made it possible for life to emerge here at all. And Voyager 2's data is telling us that this shield is more complicated, more porous, and more dynamically variable than we ever knew. But here's where the story takes a turn that nobody saw coming, because the most extraordinary revelation to emerge from the Voyager 2 mission in recent years did not come from its measurements at the heliopause. It came from a reanalysis of data the spacecraft collected nearly 4 decades ago during a planetary flyby that scientists thought they already understood. And what that reanalysis revealed is one of the most uncomfortable truths in the history of modern planetary science. On January 24, 1986, Voyager 2 conducted the only close encounter any spacecraft has ever made with Uranus. It flew past the planet, collected data, transmitted its readings, and moved on. Scientists analyzed what came back and reached a set of conclusions that shaped the scientific community's understanding of Uranus for the next 38 years. Those conclusions turned out to be built on a catastrophic misreading of what the data actually represented. And the reason they were wrong is so extraordinary that it reads less like a scientific error and more like a cosmic prank. When Voyager 2 flew past Uranus in 1986, the planet's magnetosphere behaved in ways that made no sense. The electron radiation belts surrounding Uranus were bizarrely intense, registering energy levels second only to Jupiter's notoriously ferocious radiation environment. But the magnetosphere itself was almost entirely depleted of the plasma that normally feeds such radiation belts. The 5 major moons orbiting within the magnetosphere, which, in similar systems around other planets, release water ions and other particles into the surrounding magnetic field, appeared to be contributing essentially nothing. Scientists looked at this data and drew the logical conclusion. The moons must be geologically dead, inert, frozen worlds with no internal activity, no atmosphere worth measuring, and nothing to contribute to the planetary environment around them. Uranus was classified as a cosmic outlier, an anomaly among the giant planets, a place where the standard rules of planetary science simply did not apply in the expected ways. That classification stuck for 38 years. It influenced theoretical models of ice giant planets. It affected decisions about future mission priorities. It gave Uranus a scientific reputation as a strange and relatively uninteresting world, certainly not a place where you might find active geological processes or moons with subsurface oceans or dynamic interactions between planetary bodies and their magnetic environments. And then, in November 2024, a research team published a paper in Nature Astronomy that demolished the entire framework, every conclusion, every model, every assumption that had been built on that 1986 flyby data. The research, led by Jaime Jaskinski of NASA's Jet Propulsion Laboratory, identified what had actually happened during Voyager 2's Uranus encounter. Just days before the spacecraft arrived, the Sun had released an unusually intense burst of solar wind. A storm of charged particles had crossed the solar system and slammed into Uranus, dramatically compressing its magnetosphere. And this compression squeezed the plasma out of the magnetosphere, stripping away the particles that should have been there under normal conditions. The intense electrons that were feeding the radiation belts came not from the moons, as would be expected under normal circumstances, but from the solar storm itself, which had injected high-energy particles directly into the compressed and destabilized magnetic environment. The depleted plasma, the supercharged radiation belts, the apparently inert and geologically dead moons, every single anomalous reading that scientists had spent nearly 4 decades puzzling over and building theories around, was the product of a rare solar weather event. An event that occurs only approximately 4% of the time. Voyager 2 had arrived at Uranus during one of the most unusual and unrepresentative moments in the planet's regular behavior cycle. And for 38 years, the entire scientific community had been treating that 4% snapshot as the definitive description of what Uranus normally is. The moons that were classified as geologically inert may not be inert at all. They may be actively releasing plasma into the magnetosphere. They may be generating the kind of particle interactions that, in similar environments around other planets, have been associated with subsurface liquid water. There may be geological activity on those moons. There may be internal heat sources. There may be conditions that fall somewhere along the spectrum of what scientists cautiously and carefully describe as potentially interesting for astrobiology. We do not know. Because in the 40 years since Voyager 2 flew past, no other spacecraft has returned to Uranus, and the one set of data we have from that single visit was collected during a freak event that fundamentally misrepresented the planet's normal state. The implications of this extend far beyond Uranus. Think about every planetary body we have visited exactly once. Think about every moon, every asteroid, every distant world, where a single flyby produced a single data set that became the foundation of the scientific consensus about that object. If a 1 in 25 solar weather event was enough to completely distort our picture of an entire planet for 4 decades, what does that say about the reliability of single encounter data from every other object we have only visited once? This is not a comfortable question. It does not have a reassuring answer. And it is one of the most important methodological challenges in planetary science today, brought into sharp relief by the reanalysis of data from a spacecraft that is currently floating in interstellar space 12 billion miles away. The cost of misunderstanding one planet at one moment in time cascades. Graduate students wrote dissertations that leaned on the 1986 Uranus model. Funding proposals pointed to it. Hypotheses about how ice giant systems work in general stretched out from it. Every one of those studies, every grant pitch, every chapter that described Uranus as a quiet, inert oddball has to be reopened now. A single anomaly in a single flyby quietly shaped the scientific conversation about a whole class of worlds for nearly 40 years. That is how fragile a one-shot picture really is. Now, layer onto all of this what Voyager 2's interstellar boundary data is telling us about the shape of the heliosphere itself. For decades, the dominant scientific model depicted the heliosphere as elongated, like a comet, with a rounded leading edge pointing in the direction of the sun's movement through the galaxy, and a long trailing tail streaming out behind. It was a clean, intuitive, visually satisfying model, the kind you could draw on a whiteboard in 5 seconds without hesitation. And it was wrong, or at minimum, profoundly incomplete. The data from Voyager 2's heliopause crossing, combined with what Voyager 1 found at its own crossing point, has driven researchers towards substantially revised models of heliospheric geometry. Some of the newer models suggest the heliosphere may be far more spherical than previously thought. Others propose structures of remarkable complexity, shapes that have been described in the research literature as resembling a croissant, formed and compressed by the pressure of the interstellar magnetic field in ways that create geometry no previous model had predicted. The 2 Voyager probes exited the heliosphere at different locations, separated by vast distances, and the boundary conditions they measured at those locations were significantly different from each other. Different thickness, different particle density, different magnetic characteristics, different interaction patterns between solar and interstellar material. These are not the minor variations you would expect from a simple, uniformly shaped boundary. They are the fingerprints of a structure far more intricate and variable than anyone had mapped. Research published in early 2024 formalized a model that further complicated the picture. The data from both Voyager crossings, analyzed in combination, supports the existence of what scientists are now calling a thick boundary layer. Not a thin, sharp transition zone, but a broad, complex intermediate region, where the magnetic fields from inside and outside the heliosphere interact in a sustained and dynamic fashion over a substantial distance. Under this framework, neither Voyager 1 nor Voyager 2 has yet reached what would qualify as truly undisturbed interstellar space. Both probes are still transiting this thick transitional zone, a region that behaves differently from either the interior of the heliosphere or the pristine interstellar medium beyond. The genuinely undisturbed space between the stars, the environment that exists beyond all influence of our sun's magnetic reach, has never been directly measured by any instrument humanity has ever built. We have never been there. We do not know precisely what it looks like at the particle level, what its magnetic architecture consists of, how it varies across different regions of our galactic neighborhood. We might find out before Voyager 2's power finally fails, or we might not. That uncertainty is real, and it sits at the center of where this mission currently stands, because the clock is running down. Voyager 2 is not dying quickly or dramatically. It is dying the way complex systems die when they are pushed far beyond their design parameters. Gradually, instrument by instrument, as the margins grow thinner and the choices grow harder. The spacecraft is powered by a radioisotope thermoelectric generator, a device that converts heat from the decay of plutonium-238 into electricity. That decay is relentless and irreversible. Every year, the generator produces slightly less power. And every year, the mission team at JPL must decide which systems are essential enough to keep running and which must be permanently shut down to conserve the remaining watts for the instruments that matter most. In October 2024, NASA made one of the most painful decisions in the mission's history. The plasma science instrument aboard Voyager 2, the very detector that had made its unique heliopause measurements possible, the instrument that Voyager 1 had lost years earlier and never had available for its own crossing, was officially deactivated, turned off permanently to conserve power for the 4 remaining functioning instruments that scientists hope will continue returning data through the late 2020s. The instrument, whose readings generated the 54,000 degree temperature discovery, whose data revealed the magnetic alignment anomaly, whose measurements demonstrated the permeability of the heliopause, that instrument is now silent. What it might have continued to find in the region beyond the heliopause and the thick boundary layer in the approaches to truly pristine interstellar space, we will never know. There's also the matter of how fragile the connection to these probes actually is, a fragility that most people are entirely unaware of, and that deserves far more public attention than it receives. The only antenna on Earth capable of transmitting commands to the Voyager spacecraft is a single dish at Deep Space Station 43 in Canberra, Australia. One antenna, there is no backup. There is no redundant system standing by. There is no alternative pathway for sending instructions to the only two human-made objects currently operating in interstellar space. That single dish went offline for essential upgrades from May 2025 through early 2026. During that entire period, engineers could not send new commands to Voyager 2. Whatever instructions had been uploaded before the antenna went dark had to carry the mission through months of silence with no ability to intervene, correct course, or respond if something aboard the spacecraft went wrong. The fact that this is the situation, that two spacecraft drifting through interstellar space are connected to Earth by a single point of failure that can be knocked offline by scheduled maintenance, should register as extraordinary. These are not resilient systems with multiple redundancies. These are two ancient machines hanging in the void. The thread connecting them to the civilization that built them is far thinner than the headlines about their discoveries would ever suggest. What makes the whole situation even more remarkable is the sheer improbability of the instruments still functioning at all. The particle detectors aboard Voyager 2 were designed, tested, and certified at the Johns Hopkins Applied Physics Laboratory for a service life of approximately 500,000 mechanical steps. By the early 2020s, decades past their design specification, those detectors had completed nearly 8 million steps, 16 times their certified operational limit. Still generating data, still transmitting readings, still surprising the scientists who sit down to interpret what comes back across 12 billion miles of vacuum at 160 bits per second. There is no engineering explanation for why these instruments continue to function at the level they do. There are theories, careful assessments of the operating conditions in deep space, where the absence of atmospheric moisture and temperature cycling may have preserved components that would have degraded far more rapidly in a terrestrial environment. But theories are not explanations. The instruments should not work as well as they do. The fact that they continue to work is one of the quiet miracles sitting at the center of this mission. Voyager 2 also carries something that transforms it from a scientific instrument into something that resists easy categorization. Attached to the spacecraft's exterior is a gold-plated copper disc, 12 inches in diameter, encoded with 115 images of Earth and its life, greetings in 55 human languages, the sounds of surf breaking on a shoreline, wind moving through trees, thunder rolling across the sky, the music of Bach, Beethoven, and Chuck Berry, the recorded brainwave patterns of a woman in love, the sound of a mother kissing her child goodnight. Carl Sagan, who led the effort to create and include the Golden Record, described it as a message in a bottle cast into the cosmic ocean. A gesture made not with any expectation of success, but because it was the right thing to do. Because a civilization capable of sending a machine to the stars ought to say something about who it is and where it came from. Voyager 2 will never reach another star system within any time frame that is meaningful to human civilization. Approximately 296 years from now, it will pass within roughly 4 light-years of Sirius, the brightest star in Earth's night sky. It will not arrive there. It is not aimed there. It will drift past a fragment of a civilization that by then will either be utterly transformed beyond recognition or no longer exist in any form that would recognize itself in the images encoded on that disk. The record will outlast the civilization that made it. It will outlast the species. It will drift through the interstellar medium for billions of years, carrying the sound of a child being kissed goodnight, into a darkness so vast and so old that the concept of night no longer has any meaning. What Voyager 2 is doing right now at this moment is traversing that thick boundary layer beyond the heliopause, the complex intermediate zone where the sun's long magnetic reach finally begins to release its grip on the surrounding environment. Scientists believe the transition to truly pristine interstellar space, the undisturbed medium between the stars, still lies ahead. The data still arriving at the Deep Space Network's antennas suggests both Voyager probes remain in a region where the sun's influence is still measurable, still shaping the local environment in ways that distinguish it from the galaxy's background conditions. What lies beyond that final transition has never been directly measured. No instrument built by human hands has ever been there. We do not know what it looks like. We do not know what its magnetic architecture consists of. We do not know whether the models we have built to describe it will hold up when the data finally arrives, or whether they will fail the way the models of the heliopause failed, the way the models of Uranus's magnetosphere failed, The way every confident framework this mission has encountered has eventually been forced to make room for a reality more complex than the one it was built to describe. There is a version of this story that ends with a triumphant summary of what humanity has learned, but that version misses what is actually happening here. Because what Voyager 2 is really revealing, what the accumulated data from 47 years of uninterrupted transmission is quietly demonstrating, is not just a set of discoveries about plasma temperatures and magnetic field alignments and heliospheric geometry. It is something more fundamental. It is the repeated, consistent, almost systematic demonstration that the universe does not organize itself around the convenience of our models. Every time a boundary has been reached, it has turned out to be more complicated than expected. Every time a question has been answered, the answer has opened two new questions beneath it. Every time scientists have been confident, the data has introduced a new reason to be less certain. And every time a model has been updated, the update has not simplified the picture. It has made the picture stranger and richer than the one it replaced. The machine is still going. The data is still coming. And somewhere out in the darkness, beyond the edge of everything we have ever mapped, a 47-year-old spacecraft built on technology that your phone could simulate in an afternoon is drifting silently outward, transmitting at the speed of a 1970s modem, carrying the sound of a mother's kiss toward stars it will never reach, still finding things we cannot explain, still asking questions we do not yet have the tools to answer. And what its final transmissions will contain, whether they will arrive before the power fails, whether they will confirm the models or overturn them one last time, nobody knows. Not the scientists at JPL, not the researchers publishing papers in the world's most prestigious journals, not anyone who has dedicated a career to listening to what this machine whispers back across the void.